Welcome to Stars LaunchPod, where we chat with innovators who are overcoming challenges, pushing boundaries, and collaborating to make space more accessible and sustainable for humanity, one launch at a time.
It's one small step for man.
Here's your host, Susan Wise.
Hi, and welcome to Stars LaunchPod, Space, Technology, and Research Sciences, brought to you by starsciences.org, where we connect, collaborate, and accelerate. I'm your host, Susan Wise. And joining us is Dr. Marshall Porterfield, a professor of agricultural and biological engineering at Purdue. His research focuses on biosensors, bionanotechnology, and space biology. Hi, and welcome to the show.
Hi, Susan. Thanks so much for having me here today.
It's great to talk to you. We'd like to learn a little bit more about you real quick if you could, and also let us know what you're working on right now to help further the space industry.
Well, my main project right now is we're actually building a mission payload experiment that'll fly on Artemis III that'll be deployed on the lunar surface. So our experiment is called the LEAF experiment, Lunar Effects on Agricultural Flora. We have several plant species we'll be cultivating on the surface, and there'll be a return module where we're going to get plant samples that'll be returned back to the Earth. We'll analyze that for really gene expression changes in spaceflight to try to understand how the plants are responding to that lunar radiation environment. And then we'll be able to, share that information with with researchers back here on Earth about the kind of challenges that we're going to be facing when we go to the moon.
You know, we want to be able to make our own food while we're in space or on the moon or Mars or wherever it ends up being.
Well, we're going to have to, if it's actually going to be viable to have these kinds of missions. And we really don't know that much about the radiation environment beyond low Earth orbit. People think that, the last 20 years of research on the ISS has solved all the problems to go beyond low Earth orbit, and they really haven't. Because actually one of the restrictions in low Earth orbit is the fact that you're still shielded by the Van Allen belts and at that inclination where they orbit. So we haven't really had, that's a good thing because that has allowed people to go up to the ISS for 6 months at a time, a year at a time, but we're not anywhere near being able to support humans on those kinds of missions to the lunar surface. Only 19 people have actually been outside of the Van Allen belts for any period of time. And those were the Apollo astronauts from, decades ago. So we still have a lot to learn about that radiation environment and how we're going to protect crew health. So in some ways, the plants are going to be an analog, a biological system that we can really grind up, and study to try to understand what's happening in that spaceflight environment.
Curiosity for Artemis, what are your types of plants that you're going to be testing? What are we going to eat?
Well, we're flying Arabidopsis and Brassica. Brassica is where you get rapeseed oil from. And there's a lot of interest in working with duckweed because it has high protein content and it's very productive. So we want to try and work with some of those plants too, if we can. But we're still building the payload and, dealing with some of the challenges for how you actually do an experiment in the context of a lunar exploration architecture. It's very different than doing work on the ISS.
When you mentioned challenges, what was one of your biggest challenges and how did you overcome it?
Well, one of the biggest challenges I think I faced in my career is at the time I was at headquarters when we were starting to stand up GeneLab. And really, because what we were doing was so different in terms of how that changes the approach to how we do research in space, that there was a lot of pushback at the time from the scientific community, not really understanding how GeneLab was going to actually enable future research. So that was during the time when I was at headquarters. And since then, that's actually, GeneLab has actually been able to support a large number of meta-analysis studies that allowed us to really kind of go back and look at all the previous spaceflight experiments and pull those results. Because GeneLab is basically a clearinghouse for transcriptomics and genomics data, we're able to really do a lot more in terms of systems biology now. So, it was kind of hard to get the scientific community to come along and adopt these new standards for how we do research. In the meantime, it's really created all kinds of new opportunities for how we do research and a greater understanding for what's going on in space.
It's exciting. Yeah. What was one of your aha moments when you just went, oh, yes, this is it, or Eureka?
Oh, I've been working on several different things that over the course of my career and over the last 30 years. One of the main things I'm focused on from original work with Arabidopsis in the shuttle era was looking at mitochondrial stress and the root system. So I've really become interested in mitochondrial biophysics. So I've been working in that area for a number of years, and also developing different types of sensor technologies that allow us to understand mitochondrial biophysics. But I think meta-analysis results from GeneLab has really been providing some of that aha for me, because some of the ideas and predictions that we made 20 years ago in terms of the biophysics of the spaceflight environment are actually being validated by GeneLab. So it creates a different environment for scientific advancement when you can actually read pulling all the previous spaceflight experiments. They might have had completely different orientations of what they were studying, but if you can pull those results and put them together in the right way. So essentially, that's allowed us to really see the emergence of large meta-analysis studies that are reinforcing mitochondrial stress and mitochondrial biophysics. Even on the human side, human medical side, we know that that's one of the primary drivers for biomedical stress in the spaceflight environment. So it's really kind of a accumulation of seeing the meta-analysis studies at Purdue and GeneLab, and seeing the emergence of you can pull out of the data from these data.
These experiments also can do with, spaceflight astronauts, but also lead to applications right here on Earth. Yes.
Well, yeah, the original approach that we started laying out in terms of the application, how we were going to use level. So when I was at headquarters, the two main initiatives I started were GeneLab, and on the human medical side was really the Twins initiative, because that was the first foray into human genomics. So yeah, the creating, the experimental platform to do those tools, really we're pioneering precision medicine. And if you think about it, coming down to these critical missions with the small numbers of individuals, we do need to have precision help, because that allows us to actually optimize architecture for the medical of each of those crew members based on their own personal genome. And that's really the direction that we're going in with medicine on here on Earth. But, we're going to be pioneering at the frontiers of space exploration. Like a lot of technology that's come from NASA, there's a spinoff of that.
Right. What's good up there is also good down here.
Yeah,
in many
we
ways.
have the problems we have in space are just the same problems we have here on Earth. They're just exaggerated.
Yes. What would be one piece of advice that you'd like to share with our listeners today?
Well, depending on the background and perspective of our listeners, if you were a student, I would tell you to focus on physics as a foundation for biology. Moving it is very important to understand how to use physical chemical approaches, especially in this next era of space exploration. We're going to be relying on genomics and systems level information to do a lot of the biology, but we're going to have to back that up with more functional analysis tools. So more sensing and simulation tools. If you think about it, maybe there's been a moon race, and the real race is actually to who's going to build the first base on the moon. And that's been going on for 80 years, and we just slowed down. And maybe we should have been more focused on that as our exploration goals as a base commercialization, because I know that we've lost a lot of traction, momentum, being focused on humans in space as being a primary driver for how we're actually going to go into deep space and explore.
So I'd look at the technology we have now compared to, that many years ago,
Yeah, well, we have experience with the system, the ISS. A lot of those inherited from the Russian program too. So If we hadn't have been collaborating with the Russians at a critical time, that wouldn't have allowed us to make progress with our space station programs. But we haven't done as much as we should have with station in terms of developing countermeasures for human research. And that's one of the gaps, is still literally the logistics gap. How are we going to grow food? How are we going to provide life support in space? And can we use biological systems to do that in a way that's sustainable? So those are the critical issues, and we still haven't answered any of those questions. So those are still part of the major focus of our expansion into the frontier.
And about water and moisture and getting that from the air. And what do they say? Yesterday's coffee is today's coffee, right?
Yeah. Well, yeah, we're going to have to use waste to be a really important part. One of the problems with the water system they have on the ISS, while it was a development of the best technology that we want to take with us beyond ISS, because a lot of the up mass for the consumables that are required for that water recycling system are actually, there's more up mass for those consumables than there would be if they just brought water up there. So that's one of the things we're looking at, is how to use waste materials and potentially lunar regolith. So we're actually looking at using those materials to print materials that we can use for mushrooms, like these different types of bioceramics we're developing now. So we could print this from human waste streams and from lunar regolith, and we'll be able to turn around and use this as a water filter. But essentially we're making lunar ceramics. That's how we're going to colonize the moon.
All right. Hey, if it works, I like it. Dr. Porterfield, before we wrap up, if you have a passion project, either past or present, that you would like to mention.
Oh, well, I'm really focused on actually developing a single mitochondrial recordings. I want to be able to study mitochondrial systems the same way that we study single cell systems today. I think because that's really one of the areas to be advanced.
This is very exciting, and we will be following you and watching you and excited for Artemis. That's coming February, right?
Well, that's going to be scheduled for 2027 for Artemis III.
Artemis III. Okay.
Yeah.
Yes. All right. Well, that's exciting. So we'll be watching and hoping to learn. And thank you so much for sharing your story with us today.
Thank you so much. I really enjoyed getting a chance to talk to you and your audience.
Be sure to join us where we connect, collaborate, and accelerate. And we'd like to invite you to join starsciences.org. Just get a free one-year membership by entering the promo code FRIENDS321. If you enjoyed this episode, leave us a review and subscribe.
Don't miss an episode. Subscribe on your favorite streaming platform. Watch us on YouTube and follow us on social media. Stars LaunchPod, propelling us forward, one launch at a time.